Dear students, today we will be studying about the oxidation states of transition elements or their variable valency. আজি আমি সংক্ৰমণশীল মৌলবিলাকৰ পৰিৱৰ্তনীয় যোজ্যতা বা সিহঁতৰ ভিন ভিন যোজন ক্ষমতা দেখাবৰ যি ক্ষমতা থাকে সেই বিষয়ে আলোচনা কৰিম। কিন্তু সেইটো কৰাৰ আগতে আমি জানি ল'ব লাগিব সংক্ৰমণশীল মৌল বা ডি বৰ্গৰ মৌল কাক কয় আৰু যোজ্যতা মানে আমি কি বুজো। Definition of falopra, if we want to define transition element, then transition elements are those elements where the last electron enters the penultimate D cell. Okay, and another definition of transition element is that they are those elements who in their common oxidation state have incomplete D cell. সংক্ৰমণশীল মৌল বা ডি বৰ্গৰ মৌল আমি তাকেই কওঁ যাৰ ইলেক্ট্ৰনীয় সজ্জা লিখি যাওঁতে একেবাৰে শেষৰ ইলেক্ট্ৰনটো এটা ডি খোলত সোমায়। এছ বা পিত সোমোৱাবিলাকক আমি মুখ্য মৌল বুলি কওঁ আৰু ডি গ্ৰুপত সোমোৱাবিলাকক আমি সাব গ্ৰুপত থওঁ, সহমৌলৰ বৰ্গ বুলি থওঁ। So what is exactly valency? So valency is the combining capacity of an element. You will find that in the periodic table, none of the elements exist in the atomic state. Okay, none of the elements exist in the atomic state, rather they will be in the compound formation. For example, hydrogen will give you H2, HCl, H2O, etc. Lithium will be we will get it as lithium oxide, lithium chloride, lithium nitrate, etc. Beryllium chloride, magnesium oxide, magnesium chloride, magnesium nitrate, whatever be the element you take. For example, iron you will get as FeO, ferrous oxide, ferric oxide, carbon as carbon tetrachloride, carbon dioxide, carbon monoxide. So apart from these, the ideal gases, none of the element in the periodic table will exist in the atomic state. Rather, they will be in the compound formation, and that compound formation can take place either by formation of covalent bond or by formation of ionic bond and so on. So actually when we look into the periodic table, there you will find certain numbers. You see, these numbers for a main group element actually indicate their valency or combining capacity. Okay, 1 and 2 are the valencies of this element, and that is why for group 1 you have lithium chloride, sodium chloride, KCl, RbCl, cesium chloride, etc., where all of them shows a valency 1. Okay, in the second group, for example, if you go for it, you will have all the elements showing the valency 2, fixed valency, no change in valency. For example, if you go for magnesium, this particular compound, magnesium oxide, then someone may say here it is combining with only 1 electron. How can its valency be 2? So magnesium is what? Magnesium is neon 3s2. Okay, neon 3s2. So magnesium, if it wants to release 2 electrons, then immediately it will be having the neon configuration. So magnesium would like to go to magnesium plus 2 state. Oxygen atom has atomic number 6. Oxygen atom has atomic number 8. So if it can take 2 electron, immediately it can go to O2 negative, that is neon configuration. So it will be an ionic compound magnesium oxide where magnesium is plus 2, oxygen is minus 2. So this 2 is the valency. Anyhow, when you take the main block element, whatever be their group number will be their valency. Clear? And for these elements, their group valency is given by the number 3, 4, 5, etc. Not 13, 14, 15. So boron you will be having as boron chloride, aluminium trichloride, gallium trichloride, carbon 4, so it will be having the valency carbon tetrachloride, silicon tetrachloride, germanium tetrachloride. It is fixed. For this element, actually, this 5, 6, 7 after carbon, the valency is actually 8 minus the group number. 8 minus group number. So this is 15. This 5 you take out. 8 minus 5 is equal to 3. So for nitrogen, you will be having NCl3, valency 3. But for phosphorus, you can simply go to the group number. It is 15, take the 5. So PCl5, ASCl5. Then oxygen, the 6, 8 minus 6 is equal to 2. You have the valency of oxygen is 2. But you go to the next number, that means sulfur, it will show the valency 6. Okay, so when we are concerned with the main block element, main block means this S block and this P block. This P block and S block, if we consider, then their valency is given by this group number and their valency is fixed. But when we go to the transition element, in my last video I show you that 1s, 2s, 2p, 3s, 3p, 4s, 3d. This is on the basis of energy. This is the orientation on the basis of energy. But on the basis of valency, if we want to arrange them, this will be 1s less than 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. Why this is so? Because here n is equal to 1 for cell 1, n is equal to 2 for orbital number 2, n is equal to 3 orbital 3, and n is equal to 4. So this will be the valence cell, okay, and n is equal to 3, this will be the penultimate cell. For these elements, it is the penultimate D cell which starts filling. So the configuration for transition element is found to be, the general configuration is n-1 D 1 to 10 and S 1 to 2. Hence, you will find that this particular transition element, instead of showing only one valency just like the main block element, is found to show some different valencies. For example, if you go to scandium, okay, what is the scandium configuration? Scandium is 21. Hence, if you arrange electron 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. This is on the basis of increase in energy, okay, increase in energy. But if you go to valence cell configuration, then the same configuration turns out to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. And above that, this is 4p0. You can write that also, 4p0. Okay, 4p0. Okay, now you see up to this is argon configuration. Okay, up to this is argon configuration, and hence you can write scandium as, scandium is equal to argon, this 3d1, 4s2, 4p0. Or if you write in terms of orbital, then this is argon. 3d means it is the combination of 5 orbitals, clear? And this is 4s, this is 3d, and this is 3, 4p. And electron will be here, you will be having 2 electron, and for scandium you have this. Now the thing is that scandium will never ever exist in this particular form, rather it would like to go to the nearest noble gas configuration. So in scandium we will be having 1 electron in the penultimate D cell, and this is 4s2, 4p0. D orbital is a combination of 5 different subcells because they have different ml values. This is -2, this is -1, 0, +1 and +2. Now, if scandium exists like scandium atom, then this is okay with this particular electronic configuration. But instead of this, we have scandium in a compound formation. Why scandium will go to compound formation? Because it wants to have the nearest noble gas. Now for scandium with atomic number 21, it can go to 2 noble gas configuration. Either it can go to 36 krypton or it can go to 18 argon. If scandium wants to go to argon configuration, it will have to release 3 electrons. On the other hand, if scandium wants to go to 36 krypton configuration, then immediately it will need 36. So 36 minus 21, it needs 15 more electrons. Okay. So one process means it will have to add electron. Okay, to go to 36 krypton, and the other process means that it must remove electron or release electron to go to scandium configuration. Now what it can do? It has been found that if you go to the periodic table, that transition elements are actually called transition metals. Okay, transition metals. Now, what does metal mean? Metal means that metals are those who can only be in positive oxidation state. Metals are those who can only be in positive oxidation state, means a metal can release electron, definite number of electron, to go to metal plus n state, but metal can never ever accept at least one electron to go to the negative state. Why? Because metals have very low ionization energy but very high electron affinity, a very low electron affinity, and neither they have high value of electronegativity. Very low ionization energy, as well as ionization energy means the energy required to remove the outermost electron from their valence shell is very low. So they can release electron but they cannot accept electron, because even though they need electron, they cannot accept electron to go to negative oxidation state. Okay. Now, there is another thing, that these are called transition. That transition means flow. Transition means flow. Ahomiyat koa hoy সংক্ৰমণশীল মৌল. সংক্ৰমণ মানে হুচৰি যোৱা. You see that these transition elements or the D block elements actually falls in between the S and the P block. Okay, so the S block, these are actually pure metals and these are actually pure non-metal. They are called transition. This is only because of the fact that there is flow of property from S block and from the P block to the D block. Now, what are S block element? S block are all metal. They are very hard with high boiling point and melting point. They have very low ionization energy, very low electron affinity, very low electronegativity, and the alkali metals always form the ionic bonds. Clear? Ionic bond means they prefer to go for ion formation. Now, what is P block element? If you consider that the P block elements actually are those elements where the last electron enters the P block, P orbital, and they prefer to go for covalent bond formation, and even if they go for ionic bond formation, they will form the anion. Okay, they will form the anion. What does that mean? That the P block element can easily go to the negative oxidation state by accepting electron, be it oxygen who can easily take 2 electron to go to 2 negative, be it halogen who can take immediately 1 electron to go to this particular state. So those P block elements prefer to go to negative oxidation state. This S block element prefer to go to a positive oxidation state, and in between this D block shows the property of both S as well as P. They prefer to go to ionic bond formation, but at the same time they can form coordinate covalent bond also, not direct covalent but coordinate covalent bond. But one thing is for sure, that this transition element will never ever go to negative oxidation state. So if you go for scandium, then scandium with by accepting electron to go to krypton configuration, these you cannot think to happen. Scandium will never ever accept electron to go to krypton configuration. Then what will be remaining? That scandium must release 3 electron to go to argon configuration. Okay, so what is the problem then? You can remove 3 electrons, but you see that these 3 electrons are in 2 different orbital. So again we can see that in scandium we have 3 electrons. If we can release these 3 electrons, it can go to the argon configuration. Clear? Now where these 3 electrons are located, unfortunately these 3 electrons are not in the same orbital, rather in 2 different orbitals. Same is the case with titanium. It has 4 electrons before it can go to argon configuration, and it will have to release this 4 electron, but these 4 electrons are into different orbitals, that is 4s and 3d. Now what is the difference then? Why we cannot release the 3 electrons easily from the scandium? This is because if we want to remove the electron, then you must heat it from outside. Heat it from outside with a force, because these electrons are not as such, they are in constant attraction from the nucleus. The nucleus will constantly attract these electrons towards itself. So if you want to remove the electron from the attraction of the nucleus, then you must provide energy from outside. Clear? So if we want to remove electron from the attraction of the nucleus by providing energy, this means we have to aim the electrons and then heat. Now if you can see this electron at one time, you cannot see these 2 electrons at the same time. The electrons will obviously be removed from the outermost cell. So first the 4s electrons will be removed, and then you have to go to 3d, because this is valence, this is penultimate. These 2 electrons, since they are in the same orbital, if you strike this electron, they will be removed at once. But when you are looking to this electron at the same time, you cannot go for the 3d electron. What does that mean? This means that we will have to release the electron one by one. Suppose you have scandium, you have argon, then the penultimate is 3d1 and the outermost is 4s2. So first of all, we have to heat this electron. Okay, we have to aim these electrons so that we can remove them, and hence you remove the scandium. Okay, 2 electrons will be removed and you will be having the scandium plus 2. Now the thing a little bit differs from the sense that you see scandium originally had 21 electron and 21 proton, that is its atomic number. Okay, now once it goes to scandium plus 2, then in plus 2 state, scandium now will be having 19 electron and 21 proton. Proton at the nucleus, so it will remain same. The number of electron is decreased. Once this is decreased, the 21 proton which originally attracted 21 electron, okay, in the neutral, scandium, now in scandium plus 2 state, immediately the electron number is decreased. It is 19, but the proton number is 21. So in scandium plus 2, this d electron will be attracted by even more higher force. So you will have to wait for some time. Okay, wait for some time. That means you must bring energy again to remove the d electron, and then only you can go to this particular state. Okay, there will be a time difference. Once you thought that I had 3 electron, I can remove them, but once you remove this electron, you suddenly the attraction of the 19 electron by the nucleus increases to such a level that you have to wait for some time to bring the energy, because until and unless you provide ionization energy, it will not be removed. This will be attracted by the nucleus. since you will have to wait for some time, this means that the time you wait for bringing the ionization, proper ionization energy to remove the electron, that time, for that particular time, the +2 state will be stable. Yes. So argon with the configuration 3D1 4s2, you have to have ionization energy to release electron, and previously you thought that you have 21 electron and 21 protons. So for 3 electron you consider this condition. So scandium will release the 2,4s electron, will go to scandium +2, and then scandium +2 will release the next electron to go to scandium +3. But unfortunately, from going to scandium +2 to +3 state requires higher amount of energy, as now the number of electron is 19, but the number of proton is still 21. Since you have to wait for some time, this means this will be stable for certain time. If this is stable, we know that ion cannot stay as such. Since ion cannot stay as such, then immediately scandium +2 will need some anion to stabilize it. So scandium releases 2 electron to go to scandium +2. At that time, that 2 electron must be accepted by someone, because if this is oxidation, this will be reduction, and without reduction, oxidation cannot occur. So you will be having 2Cl negative. We know that this is not having the argon configuration, but still this is formed, and immediately scandium plus 2Cl means Cl2 will give rise to the compound ScCl2 with scandium in +2 state. Now what is the combining capacity of scandium here? It will be 2. Why this is formed? Because in order to go to argon configuration, first scandium will have to release its s electron, and since in doing that you have to wait for some time to go to again +3 state, so immediately for that particular state the condition that the +2 state of scandium must be stabilized, and doing so, while stabilizing the scandium in that state, you have this particular compounds ScCl2 or ScCl2, where scandium in +2 state, chloride in -1 state. Now, once this is formed and you have enough energy to remove the last electrons from scandium, now you will be having scandium +3, and to stabilize that particular state, you will be having another compound called ScCl3. So, for scandium, you are now having two different compounds. Two different compound for the same element. Now, what is valency? It is the combining capacity. What is the combining capacity of scandium? It shows two combining capacity. One is ScCl2 and the other is ScCl3. Here the valency shown is +2. Here the valency shown is +3. So, is it a fixed valency for scandium? No. It is not fixed valency for scandium, just like alkali or alkaline earth metal. Rather, it shows more than one valency. If someone asks you why this is so, this is because scandium, in order to go to inert case configuration, must release its energy, electrons from outside. But unfortunately, in case of scandium, the outermost electron is not present in the same cell. It is present in two different cells. What are the two different cells? One is the penultimate D cell and the other is the Helen S cell. Now, scandium, to go to argon configuration, must release electron from two different sets. But we cannot remove electron from these two different orbitals at one time. Okay, we cannot remove these electrons at one time. This is because of the fact that both of them have different directions. Both of them have different directions in space. So you have to aim them one by one. First, the valence 4s orbital will release, and then only we can go to the penultimate set. So this is the case, and hence we have to wait for some time. After removal of the s electron, then only we can go to d orbital, and within that time the two states will be stable. So we can say that why transition element shows variable valency. Transition element shows variable valency because of the fact that they have outermost electrons in two different orbitals before they go to argon configuration. All of them can go to argon configuration by removal of the electron present in them. Here 4s is the outermost, 3d is the penultimate. Now before doing that, here you see that there are 2d electron in titanium. So first of all, titanium if I take, then titanium will remove its 4s electron, 4s2 electron to go to titanium plus 2 state, okay, and then only it can remove the d electron one by one. So titanium plus 2 will remove another electron to go to titanium plus 3 state for some time, and then only it can release the second d electron. From titanium plus 3 it will release another d electron to go to titanium plus 4. So titanium goes from plus 2 plus 3 plus 4. All these states are shown by it, and while showing these states, it will form definitely different compound. For example, titanium dichloride, titanium trichloride, as well as titanium tetrachloride. Now more than one valency for the same element. This is not the case with S block or P block, but for D block we will be having this scenario. Hence, we can say that for S and P block, even though we have the fixed valency, for transition elements, we do not have fixed valency. First and foremost, any transition element cannot accept electron to go to the nearest noble gas configuration. Rather, they will release electron to go to the inert gas configuration. While doing so, while releasing electron, they have to release electron from two different orbitals, S as well as D. Since these orbitals have different orientation in space, that is why they have to release one by one. And while doing so, the ionization energy increases from one to other level, and hence they have to wait for some time to bring the required amount of energy to release the next electron. So for this waiting time immediately gives rise to the formation of a compound. Thus, scandium, as we see that it has 3 electrons in 2 different orbitals. So scandium will release these 2 electrons and will go to this particular state. Titanium has 4 electrons in it, so it will have to go for release of these electrons one by one. The 4s electron will obviously release at one time, but the 2d electrons have to be released one after another. Vanadium has 5 electrons in its valence shell, so it will have to release the 5 electrons one by one to go to the nearest noble gas configuration, and this is the case with others also. If we go for seeing the different oxidation state, then the proof is that let us take the manganese. When it is in plus 2 state, by removal of 2 electrons from the 4s cell, it is having this particular color. When manganese is in plus 6 oxidation state, by removal of 6 electrons, 2 from the s orbital and 4 from the 3d orbital, then it is having this particular color. And when manganese is in plus 7 state, by removal of 2 electrons from s orbital and all the 5 electrons from the d orbital, then it will be having this particular color. Thus, we can say that d orbitals or transition elements show variable valency because their outermost electrons are present in two different orbitals. One is s and the other is d. And the d orbital, the 5d orbitals have different orientation in space, and since they have different directions in space, we have to remove electron one by one from this orbital. If we notice this particular orbital, then we cannot remove electron from this. So this orbital releases electron one by one because of their different orientation, and hence we have different valencies for transition.